So this is Lab 2, Motion of a Falling Object. I'm Chuck Eisenhauer. This is Physics 2211, Section N05. So first things first, the problem. The problem was, is there any force besides gravity acting on a falling object? Is that its terminal velocity. So the object I picked was a small styrofoam ball. It was about the same size of a ping pong ball. So we learned that when dropping an object, following Newton's second law and the momentum principle, we see that the net force on the ball isn't zero. There's other forces acting on it. There's gravity and drag force acting on the ball. That's going to affect the ball's velocity. So in the end, my overall result was that the model aligned perfectly actually with my observed data and predicted exactly what it should have. So when I took the video, put it in a tracker, like we all know, the initial data was, my initial time was 0, the initial distance was 0.02 meters, my initial velocity was determined by the change of position over the change over time for the first 2 points. So there's the formula written out, and it ended up being, negative 0.42857 meters per second. The mass of the styrofoam ball was 4.6 grams or 0.0046 kilograms, and then the change in time, or the time step, was going to be 1/1000th of a second. So this is what the model looks like without drag. This was just gravity acting on the ball. So we're assuming that the drag constant, which is B, is 0. So there was no drag acting on the ball. So the only force acting on was gravity. So when it's falling, it's actually reaching its terminal velocity. It should be longer, it should reach a longer distance than the observed model predicted, and it did. And then when you look at the actual model, the only arrow on there is the arrow pointing down, which is gravity. You can kind of see down there at the bottom that the position is negative 0.853, which I'll show you in a second, is longer than what my observed was. So this is the code for the model with air resistance. As you can see, I put the mass up there at the top, that the mass of the ball was 0.046 seconds. There's the initial position, there's the velocity, the time was t equals 0, this is the time step. The proportionality constant to b was determined experimentally. Like, I just kept plugging different numbers of b in, judging which way to move it, up or down, to get a final position close to my observed position, which was negative 0.8811. So then over here in the code, you had to change the time. You had to account for the drag force, which ended up being this whole equation right here. The final position that I got from the model was the same as my observed position. As you can see on here, there's 2 arrows. There's the gravity going down, pulling it down towards the Earth, and then the drag force was pointing up, acting against gravity. So when you graph all those together, you can see that the drag force was lined up perfectly with my observed model. The drag force model lined up perfectly with my observed data, and gravity did not, which was expected. And gravity also went further down in position than my observed data, which also was expected. There's a curve in it. It's not a straight line like the last lab. So there's acceleration. It's not just a constant velocity. So what does this mean? It means that overall it was a pretty successful experiment. Everything seemed to line up. It followed Newton's second law and the momentum principle that said objects' change of momentum is determined by the force of the object undergoing over a period of time. And then the model without the drag predicted the terminal velocity. The reason why it's the terminal velocity is because the only force acting on that ball is gravity. If there's nothing else that's going to be slowing it down, then it's going to reach a certain point, because gravity is a certain magnitude, and it's going to just hit a maximum speed, ergo terminal velocity. So the other what if is what if it was thrown? No, the terminal velocity would not have changed if it was thrown. This is because if gravity is the only force acting on it, it's going to speed up no matter whether it's thrown or dropped to that terminal velocity. And then if drag force is taken into effect in that, then the ball actually would never, over such a short period of time, the ball would never reach terminal velocity even if it was thrown. So yeah, that's basically it. Thanks.